All right, should be recording. Let's go over exam 4, be version C. Okay, first one wants the hybridization for oxygen in H2O. So if we draw the structure of H2O, has bent geometry, and our electron geometry is 4. We have these 2 lone pairs and then these 2 single bonds. We want this to have these single bonds and these lone pairs to have equivalent energy. So we're going to have s orbitals and p orbitals. And in this case, we have 4. So we're going to have to take all 4 and make 4 sp3 hybrid orbitals. So that should be answer B. Two, how many of the following molecules are polar? We have Br, F3, CS2, CF4, and NH3. BrF3, let's see, that's going to have 28 electron groups. So we should within here have 1, 2, let's see. Oop. 18, 22, 24. We need 28, so we're going to have 2 lone pairs on that bromine. It's going to push those fluorines down. So the fluorines are more electronegative than the bromine, and then because of its shape, it's going to have an overall polarity in one direction. CS2, it's going to look similar to CO2. It's going to have linear geometry. The sulfurs are going to be more electronegative, but there won't be any overall polarity to that molecule. And the CF4 is the same way, where the fluorines are more electronegative, but this is tetrahedral. Because they're all equidistant around, there's not going to be any overall polarity to that. With NH3, that lone pair in the nitrogen is going to push. There we go. Those hydrogens down. So this is going to have some overall polarity as well. So 2 of those are going to be polar molecules. Using the Vesper model, what's the molecular geometry of ICl4? Here we're going to have 36 electrons. So if I put the I here, we're going to end up that. Each of these is going to have the 6 lone pairs, or 3 lone pairs, 6 total electrons around them. So that's going to give us 24, 26, 28, 30, 32. We need 36, so I have 2 lone pairs on the iodine. They're going to end up on the top and the bottom, so we're going to end up with something that is square planar. For this one, answer C. Choose the best Lewis structure for selenium tetraoxide. Out of all of these, we want the one that's going to look like this. We should have, let's see, selenium is going to be element 34. It's got 6 valence electrons, so we have that around. So we have what, 6 times we have 30 total electrons. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 2, 4, 6. Wait, did I overcount? Let's see, 6 and 6 is 12, and 8 is 20, 2, 4, 6, 8, 32. And we wanted, oh, we have that 2 minus charge. So that's right, it'd be 30, but we have the 2 minus charge. So, yeah, 32 total electrons. So there's our 32 accounted for. Selenium can have an expanded octet, so it's okay, and it has like 6, right? 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So it's got a formal charge of 0. These oxygens have a formal charge of 0. Each of these oxygens has a formal charge of 1. So 0 plus 0 plus 0 plus the -1 and the -1 gives us our -2 that we're looking for there. So that should be our structure. And then technically that would resonate between having the double bonds to the left and the right and top and bottom. But out of all the choices, this is the correct one. This is the only one. That was choice C. It's the mass of NO2 contained in 11 liters at 4.58 atmospheres and 485 Kelvin. And this was NO2. So we're going to have the 11 liters times the 4.58 atmospheres divided by 0.08206 liter atmospheres per mole Kelvin times the 485 Kelvin. This is going to give us our number of moles. 1.2658. And then we know that this is NO2 gas, so we're going to multiply that by 46 grams per mole. That should give us, in this case, 58.2 grams. Other versions may have slightly differing numbers of liters or temperature. So you may get a different answer there if you had version A or B, but the setup is going to be identical. All right. Use the molecular orbital diagram to show which volume is most stable. So we're going to have sigma. Yeah, we'll do it like that. Sigma 2s bonding, sigma 2s antibonding. Then we have pi 2p bonding, sigma 2p bonding, pi 2p antibonding, and sigma 2p antibonding. So we have B2, boron. We're going to have a total of 6 electrons. So we're going to go 1, 2, 3, 4, 5, 6. Our bond order in here would be 4 minus 2, which is 2 over 2 is 1. We do the same thing now for, we can keep these, N2, 2 plus. Now each nitrogen has 5 electrons. We have 2 of them for a total of 10, but it's 2 plus, so we're only going to have 8. So that's going to be 1, 2, 3, 4, 5, 6, 7. Oh, man. There we go. That's what we wanted. 7, 8. So now our bond order is going to be 1, 2, 3, 4, 5, 6 electrons in bonding orbitals, 2 in anti-bonding orbitals. So 3 divided by 2, which is 4 divided by 2, which is 2. do the same thing for the carbon 2+. Carbon is normally going to have 4 electrons. 2 of them would be 8. But in this case, we're only going to have 6 because we're 2+. So the bond order for the carbon 2+ would be identical to the B2. And then lastly, we have C2, 2-. So again, each carbon has 4 times 2 is 8. We have 2- charge, so plus 2 is 10. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the C2, 2- is going to have 1, 2, 3, 4, 5, 6, 7, 8 electrons in bonding orbitals, 2 in non-bonding orbitals for an overall bond order of 2. That we would predict would be the most stable right there. Which compound is the strongest carbon-carbon double bond or carbon-carbon bond? Sorry, so we have H3, CH, CH3, CH3. So each carbon here has 3 hydrogens bonded to it and then can only have a single bond to the other carbon. We have CH2, CH2. So that's going to look like that. We're going to have a double bond, and the H, CCH. Is going to look like that. So which one is the strongest bond? The one with the triple bond there. Place following order in order of decreasing magnitude of lattice energy. So we have K2O, RB2S, and Li2O. So the closer they can get to each, so we've got all +1 charges here, and then on the cation, and then a -2 on the anion. So the magnitudes of charges aren't changing. We're just looking at how close can each of these get to each other. This one was meant to be an oxygen, but it shouldn't matter. If we go from lithium to potassium to rubidium, the cation is going to get larger and larger and larger. So what we should see is the potassium can get closer to the oxygen than can the lithium, which can get closer than can the rubidium. So we're going decreasing. So the the lithium is the smallest. It can get the closest to that, followed by this, followed by that. So that was a yes. All right. Consider the molecule. So we've got, well, this big molecule here. I'm going to leave out some of the incidental parts. This is CH3, which means we've got to have 3 bonds there. So we're looking at, there we go, carbon 1, which is, yep, this guy right here, and carbon 2, this one right here. So if we take carbon 1 and we just focus on it, there it is, with a double bond over here and a single bond here and a single bond here. So because of that, there's no lone pairs. This is going to have trigonal planar geometry. And then if we look at our second carbon over there, no. Then I've got hydrogen, hydrogen, that other carbon, that other hydrogen. Here, let's move this guy. So now I've got 4 single bonds out to everything else. No lone pairs. So this is going to have tetrahedral geometry. Place the elements in order of decreasing electronegativity. So we have fluorine, tellurium, and nitrogen. So we want to go from most electronegative to least. Fluorine is the most electronegative element, and then we essentially base everything on what's closer to fluorine. Next would be oxygen and then chlorine. Nitrogen is much closer to fluorine than is tellurium. So this should look like that. Define electronegativity. Electronegativity is something similar to electron affinity. Essentially, how much does that atom like electrons, or how easily can it attract those electrons to itself? So that would be answer E in this case. Which element can expand its valence shell to accommodate more than 8 electrons? We are looking for something in the third row or lower. Oxygen, nitrogen, fluorine, second row elements. Tellurium, however, is in the fifth row, so it can definitely have access to the d orbitals, so it can expand its octet. Okay, here comes the question I didn't like. So we've got BF3, BIF2, and BClF2. We don't know which has the increasing dipole moment. So if you're looking at just within the bond, this boron to fluorine dipole is the strongest. But if you're looking at it as a molecule overall, because they're all fluorine atoms at equal angles around here, this would end up having no net dipole moment. The BIF2, iodine's electronegative, the fluorine's more electronegative though, so the dipole moment on the fluorines here is going to be stronger than the iodine, and then the iodine weaker, and then what that's going to do is it'll give you a net dipole, and then the same is true for this one, although the chlorines are more electronegative than the ions, so less of a net dipole. What I ended up doing for this one is just giving all the credit. So if you, as long as you bubbled in something, you'll get credit for this. So I think everybody got the point here for this question. Choose the best Lewis structure for BF3. So boron has 3 valence electrons, fluorine has 7, so 7 times 3 is 21. So we should have plus that 3, 24 total valence electrons. We're going to end up with no lone pairs on the boron. That is okay. It is one of the exceptions to the octet rule, so it's okay that it's not meeting its octet. It's satisfied with having just 6 electrons around it, or 3 bonds. So this should look like this, with 3 sets of lone pairs around each fluorine. So that gives us 6 plus 6 is 12, plus 6 is 18, 22, 4. So that's our overall, meets our 24 valence electrons. It's okay to violate the octet rule for the boron. That's what that Lewis structure should look like. How many pi bonds are in our HCH atom or molecule? Sorry. We'll go this way. So to make a single bond, I can have a sigma bond. So this is going to be a sigma bond. This is going to be a sigma bond. And one of these bonds to the carbon will be a sigma bond. But the remaining bonds to form a second or a third, to form a double or triple bond, that's going to have to rely on side-by-side interactions between those p orbitals. And so those are going to be my pi bonds. And in this case, we'd have 2. Identify the longest bond. So we can either have, whatever, the single covalent bond, double covalent bond, or a triple covalent bond. Triple bonds are stronger than double bonds. Double bonds are stronger than single bonds, which also means the single bonds are longer than the double bonds, which are longer than the triple bonds. So the longest bond would be single covalent, or the weakest as well. Which hybridization scheme allows the central atom to form 5 bonds? That's going to be the sp3d. So if we look at our S, our P, and our d orbitals, if we want to form the 5 bonds, we're going to take these total 5 orbitals here and form those 5 hybrid orbitals there. Use bond energies provided. So we have xenon difluoride plus 2F2 goes to make the xenon hexafluoride. So we know a xenon fluoride bond is 147 kilojoules, and a fluorine-fluorine bond is 159. So we're going to take bonds broken. In this case, we're going to have 2 xenon fluoride bonds. So bonds broken are going to be positive. We would normally have 1 fluorine bond, the F to the F, but there's a 2 in front of that, so we're going to take 2 times that as well. And then from that, we'll add over here our xenon fluorine bonds, but now we have 6 of them, and since these bonds are forming, they're going to be negative. So overall, we should, well, here, I'll add it so you can see it. So 294 plus 318 plus a negative 882 gets us to our final answer there. 19 of an identified Lewis structure for Br minus. So normally Br has 7 valence electrons, so that would look like that, but it's Br minus. It has to take on 1 more valence electron, and then we would indicate its charge to the outside here. So that would be answer A for this version. And lastly, we have a large balloon. It has 25 liters of, occupies a volume of 25 liters, has a pressure of 2,575 millimeters of mercury. If we want to convert, I'm going to use the conversion into atmospheres, and it's 760 millimeters of mercury per atmosphere. So we should be at 3.388 atmospheres. We're going to find out how many moles we have. Here's our ideal gas constant. And here's our temperature. We get 2.924 moles. And now we've changed the temperature and the volume, or the pressure. Sorry, so we're trying to find volume. So now the volume is going to equal And that should have gotten us to the 39.7 liters. Or if you had slightly differing values on your version, something different, maybe like 45, 87, but you set up the same way. Or you could just do the, was it PV over T to solve for this. All right, I think that's everything. Yep. All right. Again, if you think there's an error, let me know. If you think there's something wrong with the Scantron, stop by any of the office hours. We'll double check the Scantron. I would recommend going over your old exams to study for the final. I'm not going to make a practice exam. Like I said, go over the old exams. If there's a particular section or concept that you are weak on, maybe reread that in the book. Do extra practice problems for that particular concept. And that's probably your best bet, best way to utilize your time before the final exam next week. All right, I'll see you all Tuesday. Bye.